Right, so these optimization problems that we looked at today, how to solve some of these things, a lot of the equations you'll come up with two different equations, a primary equation and a secondary equation. And that happens when you need to solve one of the equations for one of the variables so that you can substitute it back into the primary equation and get rid of some of the variables. And then to find a maximum or a minimum, you take the derivative. And then set the derivative equal to 0, or where is it undefined, in order to come up with values that could be maxes and mins, or critical numbers. You need to do the first derivative test or the second derivative test in order to prove that it's actually a maximum or a minimum. So this example we did get through in class, but we'll go through it once, maybe a little bit more slowly here. So we're looking for two positive numbers that have to be positive. Their product is 192, so x times y is going to give us 192. And they said the sum of the first, so the sum of the first plus 3 times the second number, this is going to be a minimum. I call it n, you can call it whatever you like there. So two equations. This one is called the secondary equation, because we know a value for it. Right, and if I take that equation and I solve this for one of the variables, plug that into this minimum equation and get rid of either an x or a y. So I'm going to take that secondary equation. If I take that and solve for x, I have 192 divided by y, or 192y to the negative 1 if you like. And then I can take that and plug it in up here, and then I will have a primary equation that only has one variable, just have y's in it. So I'm going to take out this x and replace it with what x is equal to in terms of y. That's 3y. And now I have my primary equation, which is one variable. Now I can take the derivative. So the derivative of n is going to be n prime. The derivative of 192y to the negative 1 would be negative 192, y to the negative 2, and derivative of 3y would be 3. To find a max or a min, you set this equation equal to 0. 192 over y squared on the right-hand side will become positive. And cross multiply, 3y squared is 192. Y squared is 64, so y is going to be either positive or negative 8. But really, I can eliminate one of those answers since they told me these two numbers have to be positive. Y would have to be positive 8. So I was able to eliminate one of those options. I can go back and get the x value that goes with that. So y is 8. If I substitute back in that secondary equation, I'll have 192 divided by 8 will give me my x. So my x is 24. And then the last thing I need to do is I need to prove that what I just came up with was actually a maximum value, or sorry, a minimum value, not a maximum value. So y equals 8 gives us a minimum. So we can do this two different ways. We can do the second derivative test, or we can do the first derivative test. So here's the first one. We'll do this problem this way. So my second derivative test would be back here. I need to take my first derivative, find the second derivative. Plug in my y value of 8, I'll have 384 over 8 cubed, which is a positive value. It doesn't matter what the numerical value is. So my justification then would be something to the effect of since m double prime is positive when y equals 8, and is, well, if the first derivative, the second derivative test is positive, it means it's concave up. M is concave up. Therefore, y equals 8 is a minimum. So that's one option. The second option I could do to prove this is I could do the first derivative test, which would be to make the number line, pick a value smaller than 8, bigger than 8, plug it in the first derivative to see that I have a change from negative to positive to be a minimum. And we'll do that with one of the examples so you can see your alternative to the second derivative test. All right, let's look at the next example then. So the next problem is similar to what we did with the Cheerios in class. So this one's an open top box, rectangular piece of material. We're going to cut equal squares out of the sides. So it's the same thing that we did with a different colored paper there. So now our paper is, or box, whatever it is, it's 5 feet by 3 feet. That's what we're going to start with. Now if I cut those corners off, there's some amount, and we don't know what that amount is. It could be an integer value, but it doesn't have to be. These little corners here then are some x value. So if I put this back together, I'm going to have a box that looks like this, but instead of this front side here having a length of 5, now from here to here it has a length of 5 minus the x's on the end there, one x and the other x. This side here, same thing, the whole thing was 3, but now it's 3 minus those 2 pieces I just subtracted out. And then the depth of the box is this corner right here, which is a height of x. So for this one, I'm not going to have a secondary equation because if I find the volume, that would be the primary equation, the thing that I want to maximize. If I take length times width times height, I no longer have 2 different variables. I have just one variable. Now, you can decide how you want to take the derivative for this. Usually I multiply these together because the numbers are usually not too awful to have to work with then. So 15 minus 6x squared plus 4x cubed if I FOIL these first terms and multiply by x. So now I can take the derivative. Derivative of v would be v prime. Derivative of 15x is 15 minus 32x plus 12x squared. So I have the derivative. If I set the derivative equal to 0, I do Pythagorean theorem for this one. So x equals negative b, so positive 30, 2 minus the square root of b squared, so 32 squared, which is 1024. 4 times my a is 12, my c is 15. All over 2 times a, which is 12. Right, and you can simplify. I have 32 plus or minus the square root of 304 over 24. So 2 values for x, about 2.0598 or 0.6069. And if you try to plug these values back in, actually one of these is no longer in the domain. If I have an x value of 2.05, if I plug that x value in here, that's going to make the length of that side a negative value. So this one's extraneous. If you don't see it, it's fine. When you go to plug it into your first derivative test or your second derivative test, it's going to fail. It won't give you a maximum. It will give you a minimum, or it will give you 0, something that doesn't work. So for this one, let's do the first derivative test for this one to justify that this x value gives us a maximum. So if I do that, if I plug that in for my first derivative test, you could do second derivative test. You have to do something to prove that it's a maximum. So if I do that, that's just my number line. My critical value is 0.6069. In my first derivative, I call the derivative v, so v prime. If I plug a number in smaller than 0.6069, like 0.5, if I plug in a number bigger than that, like 1, I'm looking at the derivative right here. If I plug in, I'm going to start with 1, that'll give me 12 minus 32 plus 15. 12 and 15 is 27. If I subtract 32 from it, I get a negative value. It's negative on that side. If I plug in 0.5, 0.5 is going to give me, let's see, 0.5 squared is going to give me, check my numbers here, do it the other way. So 12x squared all right, so 12.5 squared So that gives me positive 2. All right, so my graph changed from increasing to decreasing. So x equals 0.6069 is a max. My justification is since v prime changes from positive to negative at x equals 0.6069, x equals 0.6069 is a maximum. Okay, you have to write that whole sentence. Don't use the word it. Be specific as to what changed. I think they asked for the dimensions for this too, so we really need to do one more thing then. So the dimensions, if I plug this x value back into each of these 3 sides here, I would get the dimensions for the box. So if I do that, I'm going to have 1.786 feet by 3.786 feet by 0.6069. I'm going to round to 3 decimal places, so 0.607 feet.